Okay, fantastic. Thank you for coming back. Now we will hear from Giuseppe Lai, and he's coming to us all the way from Goldsmith, London. He's a PhD student working on heart-to-brain interaction and brain-computer interfaces. Okay, thank you.
Right, mouse. Okay, right. Yes, all the way from London. Yeah, thank you for having me and giving me this space to talk about what I've been working on in the past 3 years. So this is really my PhD. And today I'll be talking about heart-to-brain interaction, which is commonly known as interoception, and how we can use cardiac interoceptive information to better understand motor imagery performance and hopefully improve patient experience during non-invasive BCI training sessions. So I'll start with a research question. So this is what we asked ourselves about 3 years ago, is whether we can assume that patients, locked-in syndrome patients, are always ready to engage in non-invasive BCI training session whenever we decide, so whenever we say so. And this goes with the idea that because patients preserve conscious and cognitive integrity, they will definitely go through changes in cognition and emotion, such as motivational factor, that might really sort of affect the way they perform on a day-to-day basis during BCI training session. So what we're trying to do here is, in this project, is to extract electrophysiological markers or objective neurosignatures that can really tell us whether someone is ready to perform or ready to communicate. Obviously, this whole subject is quite a big endeavor, so we decided to start with something quite simple and narrow to understand, which is motor imagery performance, and we did this within the framework of interoception, which doesn't seem to be taken into account too much by the BCI community. So what is interoception? Interoception is really the idea that our central nervous system has evolved in a way to understand what's going on within our body. And the way that we actually see the world, or our stream of consciousness, is the result of how we sense, interpret, and integrate internally generated signal with externally perceived stimuli. This communication between the CNS and our visceral organs can be bidirectional. So it can be regulating from the brain, but also the signal that starts from within visceral organs and reach the brain. And today I'll be focusing and taking you through this journey from heart to brain. So when if we look at the heart goes through these cardiovascular oscillations. We'll start with systole, when the heart is most contracted, the ventricles are contracted, and we'll see how essentially blood is ejected within the circulatory system. And then we have the diastole phase, which is when the heart is most relaxed and blood is allowed within its chambers, right? And this is what we can see when we record this using the electrocardiogram. So we have this nice sort of ECG waveform, QRS complex, and the way that we measure systole and diastole is really given by these events of interest, such as the R peaks, the current and following, what is the mouse, current and following, and then these events down here. So this has been sort of reported in the literature on how to assess the two phases, and we use the end of the T wave to determine the transition between systole and diastole. Now, if we look closely in the heart, we'll see that the aortic arch, artery, and ventricles all contain mechanoreceptors, in particular baroreceptors, which are really sensitive to changes in mechanical forces, such as blood pressure. And what they really do, they transduce this information for the brain, and they will tell the brain about timing and strength of the cardiac cycle. This information travels via the vagus nerve and reaches the brain. So it reaches these interoceptive hubs, they're so called. But I would like to draw your attention to the somatosensory cortex. So when we train locked-in syndrome patients, or even healthy users, to use a non-invasive BCI using motor imagery, we'll tell them to focus about kinesthetic sensation, which is really the idea of trying to think about what it feels like to make a movement rather than the visual representation, so that we can engage the sensory motor cortices. So the somatosensory cortex seems to play a central role in motor imagery. So what we really try to understand in this project is whether we could find any interoceptive cardiac information that gets integrated at the somatosensory cortex level that can tell us a bit more about how this motor imagery performance really unravel through time. So before we move into the experiments, I'll tell you a bit more about this baroreceptor hypothesis, because it's really key in understanding why we care about systole and diastole within cognitive neuroscience, but also BCI. The baroreceptors are most active at systole, which is when the heart is contracted and blood is ejected. And this seems to actually influence the brain because it's injecting a lot of noise in the system, which will lead into what is known as reduction in cortical excitation, which has been demonstrated across many sensory modalities. So this leads to essentially an attenuated sensory processing, right? So you are less good at processing that information when the experimental cue happens at systole. But what it seems to be happening is that at systole, so when the heart is contracted, there seems to be a much more beneficial window for action, right? So what we're trying to do here is to find that time resolution, try to understand whether we can find a beneficial time window where we can better understand motor imagery performance. Where does it sit, right? Does it get attenuated as systole or does it get enhanced as systole? Right, so the experiment is pretty straightforward. Is inspired by the classical motor imagery-based BCIs experiments, but with the exception that we didn't show any feedback session here. So we asked 29 healthy and naive subjects to perform 50 trials of motor execution, which is really just lifting your left or right thumb based on the direction of the arrow. So pretty straightforward. We asked them to think about kinesthetic sensations and to bring them within the motor imagery experiment or blocks, which lasted for about 200 trials. And we asked them to make the movement within the first second after the cue, right? We obviously recorded EEG, CG, and EMG all sort of synchronously and concurrently. So how did we analyze our data? We obviously, after pre-processing, we use source reconstruction, in particular the linearly constrained minimum variance, or LCMV. It's a very powerful technique that allows you to sort of get rid of your volume conduction, which is a very problematic issue within EEG data analysis. So you increase your signal to noise ratio by modeling where did the signal emerge, so your neural sources. And it also allows you to collapse across these many sources and to find the region of interest, which in our case was the precentral and postcentral gyros, so primary motor cortex and primary somatosensory cortex. We obviously applied Wavell convolution, so alpha and beta, to do time frequency reconstruction. And then, this is key, we collapse across cues, so we don't have left and right cue anymore, and we obtain ipsilateral and contralateral traces. So for example, for the right cue, for the right arrow, we used the ipsilateral, the right hemisphere, and the contralateral will be the left hemisphere. And we did the same for the left, for the left cue. So how do you measure heart-to-brain interaction? So in the literature, it's actually pretty straightforward. You try to understand the binary representation between the timing of your experimental cues, in this case the arrow, and the cardiac cycle. So you really just try to find that representation in a binary way, zeros or one, right? And so that's what we did. But I will be explaining a bit more in the results section. Right, so first of all, the general effect, which is really just contrasting contralateral versus ipsilateral traces, with the idea that the contralateral trace will be, the expectation is that the contralateral trace should be much more suppressed in alpha and beta, right? What we did is to use non-parametric permutation analysis from 0.2 to 1 second after the cue. And what I'm showing here, especially, so the key is looking at this sort of green indices at the bottom, which shows us that the contralateral trace, which is the lighter shaded trace, is much more suppressed, or significantly more suppressed than the ipsilateral one in both postcentral, precentral, alpha and beta, which is great. Then what we simply do, we split our data in between systole and diastole, so it's really just a label, and you just reperform the exact same analysis. And as you can see, if we only look at systole versus diastole, you will see how the diastole is showing a much more sustained significant effects, right? But there is a fundamental issue here, and the idea is that we have many more trials in all types. By all types, I mean both systole and diastole, which is just the whole data set, and compared to diastole and compared to systole. And this is just because diastole itself, by nature, the phase, as I showed earlier, is much longer compared to systole. So naturally, by default, you will have many more trials. So we obviously control for this because we wanted to understand that this wasn't really a spurious effect and wasn't just given by the idea that we have many more trials in diastole, right? So what we did is a simple control analysis where you randomly sampled the exact same number of systole trials in both the diastole and all types distribution, which means if participant 1 has 73 trials in systole, we randomly sampled 73 trials in all types and diastole. And we did this for about 10 times. Ideally, we wanted to do more, but computational resources told us that 10 was the right sort of balance. So what I'm showing at the right here is just a summary of what we've seen earlier, just a bit summarized. So the darker horizontal bars are really just the significant indices in time, right? From 0.2 to 1 second after the Q. Now, when we do 10 runs of this randomly sampling technique, and we apply the same non-parametric analysis, what you see is that in all types, so just a sort of reduced number of systole and diastole trials, really, we'll see how the effect really sort of dissipates. It's especially in the primary motor cortex, we cannot find something similar to what is shown at the top here, right? So the all types effect. But when we do that in systole, we'll see how in the primary somatosensory cortex, especially, right, more than the primary motor cortex, this is much more resilient to the number of trials, which is really telling us that, for example, during training, if we do have reduced number of trials, rather than presenting this trial randomly, if we present them at diastole, we might have a much more sort of chance of finding effects of post-central and pre-central primary somatosensory cortex and primary motor cortex modulation, which is great. Now, we wanted to take this a step further and detach ourselves from this binary representation of simply separating your data, right, between systole and diastole. And we wanted to find that preferential window that I discussed earlier with the baroreceptor hypothesis, and whether we can find this preferential window specifically for alpha and beta. So how did we do that? First of all, we calculated this suppression index at the trial level for each participant. So really just the ipsilaterals minus the contralateral trace given the Q. So left Q, we do left hemispheres minus right hemisphere. So what that gives us is one value that can be sort of projected into this schematic sort of Gaussian distribution. If the value falls above 0, it's really telling us that has the and sort of like neurophysiological plausible effect, right? So the contralateral suppression, which is what you would expect in this motor imagery phenomena. If it falls below 0, it will be an ipsilateral type of direction, right? Which is still great, but it can be sort of split into different parts. Now, we can also embed this data by looking at the median or the 50th percentile, the 75th and the 90th, with the idea that the further we go towards the tail of the distribution, we'll have obviously less trials, but also much larger separation between the two traces, regardless of the direction. Now, what we can also do for each of this trial in this distribution, we can then find the relative position of the Q with respect to the cardiac cycle, which is really a precise timing. Where does the Q, the arrow, fall? And you can do this by using a 0 to 2 pi sort of scale and projecting it onto a unit circle, right? You can then use circular statistics to try to understand whether you have a deviation from a uniform distribution, which in this diagram can look something along this line, right? So where there doesn't seem to be any preferential timing of this Q. They all sort of uniformly distributed, and hopefully go to something more that looks more like this, right? When there is some clustering in time, and that's what the arrow is telling us. So, and just a summary of this analysis, we didn't find any effects on the primary somatosensory cortex for any of the embeddings. But we did find a significant deviation from the uniform distribution for the primary motor cortex, so the 50th percentile. So that's what we'll be mainly focusing on. So this is obviously the actual results, right, which follows that diagram that I showed you earlier, with the idea that the arrow is telling us that trials are focusing on a specific phase of the cardiac cycle. Trials that, in this case, have a positive suppression index, which is really the contralateral side of the distribution, the right side. And if we project this onto the current R peak to the following R peak, we'll see how this falls right in the diastole phase. Now, interestingly, when we look at the other side, so the less, let's say, neurophysiological, allow me the term, interesting side of the distribution, we'll see how we don't see much difference for alpha, but for beta is shifting towards the systole parts, right? And that it's actually seemed to fall in the transition between systole and diastole. And the transition was calculated precisely across using the average, right, between the end of this T wave for all across all participants. Now, what we are trying to do at the moment is try to understand how we can translate these results, which are all in the source space, right, into the sensor space. And this is an ongoing effort because obviously we cannot use source reconstructions in real time for BCI decoding. So what we have used at the moment, and this is really done in the past few months, is using the common spatial pattern, which is, really, as we know, a very good technique to allow to find spatial filters that maximize the difference between two classes. Just a very quick summary. At this point, we kept all CSP parameters fixed because usually you would optimize across participants. And what we see is that diastole has indeed a slightly advantage compared to systole. So what you see here is the number of participants that have been decoded above chance. And this chance level has been calculated at the subject, so subject specific. However, interestingly, when we look at the beta, we'll see how systole, in this case, has a much larger sort of decoding accuracy, and we see how the distribution is much more precise compared to diastole. So this is something that we're really trying to understand at the moment, and we'll, I think, very likely use more feature engineering and sort of data science approach to translate this. And obviously, we welcome any question or feedback that you might have, suggestions. The discussion, I would like to mainly focus on the baroreceptor hypothesis from a neurophysiological point of view. So I did say that research seems to find this relationship, right, between the experimental cue and when it's processed, and how do we react in terms of our neural responses to these experimental cues. Well, we do seem to find that a preferential time window it seems to be between the most noisy events of the cardiac cycle, right? The currents, the following R peak, the T and the P wave, which is kind of suggesting at the moment that it does seem that this noise generated or the less noisy phase of the cardiac cycle seems to be the most beneficial window to understand, but not decode at the moment, motor imagery performance. So what could be the applications and what could be the future steps for us? Well, first of all, obviously, we want to test this in real time, right? Because this has all been done offline and we didn't really manipulate anything in terms of the cardiac cycle. It's really just trying to find that post-hoc representation. How do we do this? We would like to use this dynamic approach, which is really presenting training cues at specific phases of the cardiac cycle and see if we can have improved learning, perhaps measured in the communication phase of the BCI. And obviously, it's not clearly stated, but also there will be a second translation, which is going into patients and see if this really can be beneficial for patients. The second idea is to use this in neurorehabilitation, specifically motor imagery rehabilitation, with the idea that it has been used for sort of stroke survivors, upper limb rehabilitation, and see whether we can, by encouraging imaginary movements at diastole as opposed to random, we can have perhaps improved neuroplasticity or improve performance, right? So output. So with this, I would like to say thank you for listening, and also say thank you to my academic supervisor and the company, Brain Control, which is the company that really funded this PhD and made this project possible. So thank you.
Thanks for your presentation. So it's new to me that heart rate or the heartbeat would determine excitability of the cortex. And can you maybe tell me, is there a behavioral effect of diastolic systolic on, like, say, reaction time or something like that? I'm just curious.
Yes, so it's something that I don't specifically have specialize in, but there is a behavioral effect in reaction time, exactly. And usually it's really how we process the experimental cue. So it's really, at this point, it's really dictated by how we process the experimental cue, and your behavioral response will be following. For example, if you see an experimental stimulus at systole, you will have an attenuated sort of reaction time, right? But I think there's also studies that really look at the how do you call it, when stimulus are presented at threshold, right? So you can increase that threshold by making it less visible or no visible. And if you present stimuli at a specific phase of the cardiac cycle, you will see that essentially participants being able to detect that stimulus at threshold much more likely. So yeah.
Thank you. I think we have maybe time for one more question, but then we really should move on. Cool. Can be short, long, anything.
Thank you for your presentation. I got it that at the moment you don't propose this as a specific means for improving the decoding quality, not yet maybe. But then on the other hand, for any kind of imagery tasks, motor imagery, whether that would be like the sensation or imagining the execution, it usually takes a couple of seconds to actually do this. So the time windows you looked at are much shorter than this. So would it have a relevance at all then? You have, let's say, 4-second time intervals for producing a certain command.
It's yeah, really good question. We started with this time window, and when we were doing the decoding, so in the past I think 2-3 months, we also started to look at different time windows when doing the decoding, and we can see how there is much more variance and how this actually changes in the last, in the last maybe, particularly in between the 2-3 second 1 to 3 second window, so right in the middle. So I think the next steps will include making this large time window and see whether that is more related maybe to the preparation of the movement rather than perhaps the actual motor execution, or motor imagery execution. So yeah, so really interesting. But I think, when you're also preparing for a talk, you do much more work in a shorter time window, right? So really the decoding is something that we're really looking at the moment, but hopefully we can find that translation and perhaps try to understand even that difference between diastole and systole that at the moment really doesn't really make sense and doesn't really translate from what we have found and looked at. So yeah, thank you.
Cool. Thanks a lot, Giuseppe. All right, so somehow we have managed to be beyond schedule, but I think it's okay. Now we will hear from Pierre about a really interesting topic of how to benchmark,
Exactly.
benchmark of how to share this data set.
Benchmark BCI decoding algorithms,
And as I understand it, then you have like a part is a talk, and then another part will allow us to maybe have a hands-on look through the through the stuff. We see where the timing takes us, I guess. I'm open to suggestions. Yeah. All right. I think no rush, and I guess we finish when we finish.
Okay. Thank you.
All right. Thanks.
Okay. Hi. So I'm Pierre Getschel. So I'm doing my PhD with Michael Tangerman here, and same lab as Jordi Tillen. So today I'm going to present you in a kind of tutorial style a library that is called Moab for mother of all BCI benchmarks. And so it's a library I use pretty much every day, and so I help build it also. And so it's a Python library that you can use to basically compare classification algorithms that we use in BCI. And so the design philosophy of this library can be summarized in this sentence, and we'll use this sentence as a guide throughout this presentation. So the first aspect of this design philosophy is the reproducibility. I don't think I need to convince you that it's important to have some reproducibility in science, but still, even if we know that, it's quite difficult. For example, a few years ago, the FreeSurfer library had an issue Basically, after a certain version, the results that you obtained were different, and they were leading also to different conclusions in some studies. And so it was not intentional, of course. And with ICA, it's also difficult to have some, like the exact same results from machine to machine. The same with eigenvalue solvers. Depending on the backend that you use, it's also non-trivial to have always the exact same result. And so it needs like a collective effort into like open source libraries to have some perfectly reproducible results. And yeah, in BCI, we're not there yet. Very often we see that the codes are not available with the papers, and people use some very strange data formats or data structures, and it's not easy to reuse their data because sometimes the data has also been preprocessed, sometimes preprocessed with errors also included. And so, yeah, it can be a huge waste of time to try to reproduce some results if everyone is doing something separately, basically. And so with Moab, we try to be a new standard for every new BCI paper. The second aspect of this design philosophy is so we're building on top of some already existing libraries. And so the Moab has two main roots, basically. The first one is MNE. I think you all know MNE. It has a very long history, a lot of contributors, a very large community. And so it's perfect for EG data processing. And the second root of Moab is scikit-learn, so which is a library for that you can use to get access to a lot of different machine learning algorithms. And it's extremely user-friendly, very easy to use, basically. And so, yeah, we have these two roots that we're basing our Moab on. And yeah. So now the core of this presentation will be, okay, how can we design such a benchmark, basically? And so these are all the components of Moab, all the components you can encounter in Moab. And the first component is the dataset, because basically, if you want to benchmark your algorithm, you need some data to benchmark it on. And so we have this dataset component, and the role of this component is to wrap some data that we find on the web, so many different data sets, and always return the same format, so an MNE row object. And so as input, we can have basically any type of data, so some math objects or some European data format or some brain vision or whatever. And we always return the same type of data to converge to like a common ground. And so we have wrappers for 16 motor imagery datasets, for 16 ERP, for 7 SSVP, for 1 CVEP, thanks to Jordi. So these are all public datasets, and the only constraint we have is that we only accept unpreprocessed data. Yeah. And so you have here a list of all the available datasets we have. And so once you have found the dataset that you want to use in this list, then it's extremely simple to use it. So you just have 3 lines. You have to import the dataset with the name that you found. You have to instantiate the dataset. And then you have to call the method getData. And that's it. And then what you get is a dictionary that is mapping subject IDs to their sessions. And so within the session, you have other dictionaries with the session ID to the runs. And within the runs, you have run names to the actual MNE row objects. And many of our users actually stop at this step. So it's a rich source of data, and you have access to many data sets and very easily. So yeah, there's nothing wrong with stopping at this step, but we can do more. And so the next component of Moab is the paradigm. And so the role of the paradigm is to pre-process the data. So it receives the raw M&E objects. It receives some pre-processing parameters, and it returns some pre-processed data, so M&E epochs, basically. And so we have different paradigms for the different BCI paradigms. Here is an example with the motor imagery paradigm, and again, it's extremely simple. You just have to import the corresponding paradigm to instantiate it with the preprocessing parameters that you want. So here there's a high pass frequency filter and 2 channels selected, but you have more parameters if you want. And then instead of calling dataset.getData, you just call your paradigm.getData with the dataset as arguments, and you get in return some NumPy array, the corresponding labels of the examples, and some metadata indicating like which subject was for which epoch and which sessions, which run, etc. You can also get some M&E epochs with just one additional argument, but it's basically the same. And so now with basically 3 + 3 lines, you have in 6 lines some preprocessed data that is ready to be given to any scikit-learn classifier. So a new addition to Moab is the caching mechanism. So we implemented this mechanism that allows you to automatically save on disk the result of the dataset, so the raw objects, or the results of the paradigm, so the epochs object. And so it's saved in a bits format, so that allows you to very easily export those datasets. So those 40 datasets that are sometimes in strange data structures or formats that we have, you can all get them in a bits format. But it's not only for export. So this caching mechanism is actually really helping for the time needed to load the data, because instead of having to load the full raw recording, you can just load the exact epochs you want, because this is what you saved. And so yeah, here's an example. If you want to save the raw data, you just have to add one parameter to the dataset.getData method. If you want to save the epochs, you just have to add this parameter to the paradigm.getData method, and same for the arrays. And yeah, so it's all taken care of for you, and yeah, it's faster. The final thing we need to benchmark some algorithms are the algorithms themselves. So it's the pipeline objects. So here we accept scikit-learn style pipelines. So here's an example of a very simple pipeline where you first compute the log variance and then support vector classifier. Without going too much into the details right now, yeah, it's extremely simple to understand and to implement your new classification algorithm in the scikit-learn framework. But if you have questions at the end, I can, of course, answer them. And so once you have selected your data set, selected your preprocessing parameters, selected your algorithm, so that you obtain some a pipeline and a paradigm, then you can evaluate your algorithms on that data with those preprocessing parameters. And so in Moab, we have 3 types of evaluations right now. So there's a within session evaluation where the data of one session is shuffled, and then we apply a 5-fold classification on the session. Coming soon, we will also have a pseudo online within session evaluation. So that will respect basically the chronological order of the example within the session. We also have cross-session evaluation. So in this case, you train on all the sessions of one subject except one of the session, and then you test on the missing session, and you repeat this for every session. And then we have a cross-subject evaluation. So here you train on all the subjects of one dataset except one, and you test on the remaining subject, basically. And so those evaluations, again, very simple. So you just have to import the evaluation that you want. So here it's the within session evaluation. You instantiate this evaluation with the paradigm that you want and the dataset that you want. And then you just have one method to call. So it's process, and you pass it a dictionary with the name of the pipelines that you want to test and the corresponding pipelines. And what you get after the evaluation is a Panda data frame that you can extremely easily export to a CSV if you want. And with these results, you can run your statistical analysis, or you can visualize your results with any library that you like. And so we already have a few visualization methods and statistical tests implemented in Moab, but you're free to use whatever you want. And yeah, that's it. And so the final point of this design philosophy is that it's community based, Moab. So we're it's open source, of course, but it's only evolving thanks to the contributors. Yeah, if you want to check all the steps that I described in this presentation, you have a notebook here. So this notebook, recreates all the steps, all the code segments that I presented you in this presentation. So if you're interested in that, I will be there right now to help you get a hand on this notebook. But yeah, if you also want to contribute into the library, you're extremely welcome. So we have, so it's all happening on GitHub. If you have questions, we'll also have a Gitter forum to answer the user questions. And we have some open issues if you want to contribute, but the main and most important always open issue is to add new data sets so that we can have more benchmarks, basically. And so if you have your own data set lying around on your computer, and you can add it, or if you know about a data set that is already open, that you can add, you're really welcome to also add it, or at least notify us. And yeah, thank you.
No. Okay, cool. Before we look at the notebook, maybe under your guidance, if there are any questions, I can keep throwing this around. Okay. Ivo.
Nice.
Coffee's empty, it's fine. Yeah, so I'm going to be running an experiment and I'll be collecting my data. But currently what I've proposed to the ethics committee is that I keep all of the recordings to myself and my colleagues that I trust. And well, this is a tricky thing, is that I am hesitant to say, like, I'll put all of the data publicly available, because I don't know what other people will be able to find in the data. So where is this balance? Because I also, at the same time, I really believe in these things. So how should I be balancing this?
I'm not sure, actually, I'm the best person to answer this, but so you can always, you have some techniques to anonymize your data. I'm not perfectly familiar with those techniques. Maybe Michael can complete later. Yeah, Yeah, maybe you can answer better that question than me.
Yeah, okay. So it has a lot of advantages to actually start from the beginning in your ethical proposal to ask for the possibility to publish your data in the end, in a fully anonymized form, of course. Now, Nick and I have been working on a data sharing agreement between Utrecht and Nijmegen, and to get the legal departments together, because that was data that was not allowed to be shared, only under very limited circumstances, patient data. And it took us half a year now to get the two legal departments working together. Now, there's a one-directional exchange of some data from Utrecht to Nijmegen. This is far from where you want to go, actually, right? So it's really a good idea to think about this from the beginning. You could possibly hand in an amendment to your existing ethical proposals, like, look, situation has changed, there would be these benefits. And I think even if there would be some findings in the data in the end that somebody else makes, it could be possibly still be a benefit for either the patient group or for that individual patient, of course, in anonymized form. But yeah, really, I don't plan any projects in any other way anymore than opening the data wherever possible. Right?
Maybe if I can, so here you have a list of 40 data sets that are open. So maybe if you browse through this list, so we have, of course, all the references of the papers that originally presented those data sets. Maybe you will find some names that are from your university and that went through the process and that can help you.
So I'm fine. I'll be able to sort this out with the university. But I wonder if I can guarantee that it won't be de-anonymized. There's also some studies that are trying to identify a person from their EEG data. So how safe am I going to be for the next 10 years? Like, I feel safe now, but if the data is still out there in 10 years, am I still safe in respecting the anonymity of my...
Yeah, it could maybe just a quick comment. We deal with data all the time, and for patients, the golden rule is if you can fully anonymize it, you can just throw it out there as long as the patient doesn't object until the moment you throw it out there, because you can't retrieve them, right? That was a huge discussion. So that's all. But anonymizing means that we, as the source, also have to eradicate any way of recognizing them. And that's impossible, because you can just take a trace, run it through all our databases, you'll find a person to do it. So, but I think that's kind of acceptable, but then your patient has to, or your volunteer has to approve that it's irrevocably published on the internet. And there's been discussions, this has been for 20, 30 years or so in neuroscience, but there's discussion, do I want someone else to find out mistakes in my code, for instance, right? And the general gist is, well, from a bigger picture, it would actually be good. And it makes you also make sure that your code, when you find something to publish, you make sure it's right. So in the end, those considerations are painful, but the bigger picture makes sense to share. And I would love to share all our patient data, but there's the European regulations that make that near impossible. So that's the struggle we have, but eventually we'll have to do this, I think.
So at Adonis, we have a lot of experience with this. We have the Adonis repository already since 2014, which was like 2 years before the GDPR became active, which started in 2016. So we have, and also the data stewards at the different donor centers have built up quite some expertise as to which data qualifies as anonymous, or what do you have to do to ensure anonymity. I also think it's not necessarily that you have like a binary, like everything fully open and perfectly anonymous versus everything closed, because it's like identifiable. There's a grayscale, and one of the things that we've done with one of the licenses under which or one of the data sharing agreements that we use a lot for the data, is that we've included a clause that also forbids the recipient of the data to try to de-identify the data. And that actually makes the lawyers much more confident that we're doing various things, because it's not only technical means that we're using to protect the data, such as like pseudonymizing, scrubbing identifiers, but that we're also using legal means. So I think you should like think along different things that you can do to protect the privacy of the participants, while at the same time like also creating the maximal impact with this data that the participants also like provide to do science with. So if you want, I can point you to the relevant snippets of information in the Donders data use agreement that might be relevant for you. And then there's the Open Brain Consent project, which might also be an interesting one for you to look at, because a large amount of this it relates to the research participant understanding what you want to do with the data. Like that forms a very important legal basis for which the data can be shared, under which the data can be shared. So it's like if you inform your participants properly, it's not only the discussion that you should have with your ethics committee, but it's the information that you provide to your research participants. And that's of course also what the ethics committee will look at.
Yeah, some of our data sets have a clause that you have to accept to be able to load the data. It's just a parameter that you have to set to true that is by default false, and it's a way to do it. Yeah.
Can I ask another question? Yeah, so you're building this, or you're making heavily use of M&E Python, but M&E Python also has itself has M&E data sets. So in what sense is this different than the M&E data sets that M&E Python already includes as like importable data sets in their tutorials? So
the issue is that those wrappers that we have, so we have basically one, so in Python, we have one class for every actual real world data set. And so this class has the job to download the data and convert it to an M&E format, because basically we have some data sets in MATLAB formats, we have some data sets in very strange formats, and then after this wrapper, we always end up with the same M&E raw object.
But is that not also what the M&E data sets as Python objects do as well?
I'm not sure.
We might want to look at this together, but there seems to like some duplication of efforts there. It might be interesting to see how much they're aligned, or how much you're actually enriching the data set, because I think that's where the difference is. That you also have the paradigm information.
We're also providing the data in with like markers that are also in a very standardized way. So if, for example, the right-hand class is always the same right_hand name across every motor imagery dataset, and the markers timing, so everything is consistent. And I don't know if that's the case in M&E or. And so this allows us to basically automatize this whole pipeline for every 40 dataset with a very clear distinction between all the components. Yeah.
So Robert mentioned that you can also share data through legal procedures. I'm not sure what these procedures are, but from what I see from that toolbox, you can download the data if you change the parameter to truth. Yeah. But everyone can do that. There's no really control, right? So I would say for now it's only for anonymized data. There's not.
So it's
there's no in between grayscale.
So I mean, not all the data is completely anonymized, I think, in MOAB, but it's also about the consent form that the participant signed, and that's the responsibility of every all the researchers that made all the studies that led to this data set. We're just using data that has been already made public, basically.
Okay, and how do you disseminate that you want people to add data sets to your?
How do I want?
How do you share it to labs and people know that they? Because
we write them an email.
Okay, I'll just.
Usually, it's also them that add their data set, because then it's it becomes much easier for other researchers to use their data, and so. Also more citations, and it's a way also to create more visibility for your data.
Yeah.
If you have the power to make it public. Yeah, Jordi added the last data set, so maybe he can give some feedback.
I mean, so in this discussion, of course, regarding the ethics, the one who is essentially opening up the data set to MOAB and to the community, I mean, they, of course, need to have obtained the ethics, the approval, let's say, to actually openly share it. If they actually breach that, then they are to blame, I guess. So you shouldn't. Anyway, I think so. In general, this is, of course, a super great effort to make data sets, the algorithms and everything very accessible and visible to the community. And it's great that this can all be done in like 3 lines of code. The downside of this is, of course, it is hiding all the complexity and all the intricate steps of the entire analysis pipeline.
Yeah.
So it might also make it more difficult.
It's also more fair between different algorithms because they all share the same preprocessing steps. And
I completely agree. But so is there also like an effort to make that transparent? And also, for instance, when I'm considering, for instance, the comparison towards in the MRI community, we have also these normalized pipelines like MRI prep. And they have this option also that they create, let's say, a text that can essentially be put into a publication that is both transparent on all the steps essentially that are involved, but also the crediting of all the, let's say, developers of specific pieces of algorithms that might be used in the background.
We don't have that like directly a text for publication, but that's a good idea actually. I'll create an issue. So getting the exact pipeline that was used to preprocess your data that you can do easily, but it's in Python code. It's not too verbose.
Yeah, the downside is, of course, if you, let's say, because you can, of course, say with all the publication that we have, we could essentially publish also the script that is like these 9 lines of code of calling MOAB pipelines and such. But then we have different versions of MOAB.
Yes.
So defaults might change. So on the background, actually another algorithm is running now. So all this documentation, I think it's something that's very valuable to the reproducibility again, which is one of the aims of.
Yeah, we have documentation online. I don't know if I can. Yeah, so the online documentation is. I think very clear, or it's supposed to be very clear, but if you find some mistakes or some things that are not clear, you can always come to me. But yeah, we have many tutorials, so I gave you a link to the first introduction tutorial, but you have many examples, and here you have the list of all the data sets with all the information that are relevant about them.
Invasive data sets are missing there.
Indeed, yeah, exactly. Yeah.
I would like to comment now with a different hat on. So I really experienced that my PhD students undergo a drastic increase in productivity using such automated tools, and MOAB is just like one of these building blocks. There's also other collections of pre-trained deep learning models or other, tools that really can increase the workflow a lot, helping the student in the end to reach publications and significant impact much quicker, taking some load off the shoulders of the student to do everything by hand. Yeah, and I think in a sense this is a starting point where we as a community start to go with the flow with what is already well established in other communities, like in terms of data sharing, code sharing, and reproducibility.
All righty. I think we can take this session maybe offline now, and those who would like to get their hands on that introduction tutorial, then Pierre will be here to guide, and maybe, I don't know, meanwhile we'll set up the posters. Okay, so thank you.
Thank you.
Okay.